Okay, you are welcome back. Now we are in session 6.6, session 6.6, which is now inverses. Okay, so if A is a square matrix and there exists a matrix A such that CA gives us an identity matrix, then C is called an inverse of A, and A is said to be invertible. A is said to be invertible. Okay, so when we have matrix C multiplied by matrix A, and we get an identity. In the previous video, we mentioned that generally matrix C multiplied by matrix A is not equal to matrix A multiplied by C, generally. Okay, but when it is equal, then it has a good property, and especially when it's now equals to I, when it is equals to identity. Okay, so when it is equals to identity, it shows that they are inverses to one another. Okay, so we can now say C is the inverse of A, or you say A is the inverse of C. So that shows instead of C, we can now write this as A inverse. Okay, this A inverse, anytime you want to write A inverse, this is how to write it. You write is a symbol to show inverse. It's a symbol to show inverse. So I can now write A inverse multiplied by A equals to I. And of course, the other multiplication, A multiplied by A inverse, will give us the same thing, which is TBI. Okay, so A has its inverse. So we call that, we say A is invertible. Okay, in the same way, we can still say A is the inverse of C. So we can write as C inverse, which is this. Okay, that means A is the inverse of C. So we can also write C inverse multiplied by C equals to I. This is an identity matrix. Also in the previous video, we mentioned an identity matrix. If an identity matrix is 2 by 2, that will be 0, 1, 0, 0, 1. That is 2 by 2 identity. Sometimes we represent it by the rank, the size. Since it's a square matrix, then we can say I2 equals to this. And we can say I3, which is a 3 by 3 identity matrix, will be giving us something like this. 1, 0, 0, 0, 1. Okay, we'll be giving us something like this. Okay, so that is I3 identity matrix. You can also have I4 identity matrix, which will be giving us 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, that is 4 by 4 identity matrix. Okay, this identity matrix, you will notice, as we have done also in the previous video, is a reduced matrix. Okay, it's a reduced matrix. Okay, so this reduced matrix is also called reduced echelon form. It's also called reduced echelon form. So with a leading one, this leading one is also called pivot. It's also called pivot. So we have a leading one, and the next leading one is to the right. The next leading one is to the right. The next leading one is to the right. And when we have a leading one, every other element in that column is zero. That is how to know a reduced matrix. Okay, so it's in a reduced form. So when we have a matrix multiplying another one, and is giving us an identity matrix, then we call that an invertible matrix, and one is an inverse of the other one. One is an inverse of the other one. Okay, for example, If we have this A, this matrix A, we have this matrix A, 1, 2, 3, 7, and we have this matrix C, 7 minus 2 minus 3, 1. And then we want to know if they are inverse to one another. Or what you need to do is just to multiply them and see if it will give us an identity. Okay, let's multiply 1, 2, 3, 7 multiplied by 7 minus 2 minus 3, 1. Okay, let's multiply these two. First, let's know maybe it can be multiplied. This is 2 by 2. This is 2 by 2. If you multiply them, since the number of column here is equal to the number of row here, then we're going to be getting the answer we're going to be getting will be 2 by 2. Okay, so let's multiply now. This row multiplied by this, we have 7 minus 6. This row multiplied by this, we have minus 2 plus 2. Okay, now we finish with the column. Now we go to the next row. This row multiplied by this, that is 21 and minus 21. This row multiplied by this, that is minus 6 plus 7. Okay, and that will be giving us 1, 0, 0, 1. So you see, it gives us an identity matrix that shows that they are inverse to one another. Let's multiply the other way. CA will be giving us 7 minus 2 minus 3, 1 into be multiplied by this 3, 7. Let's try CA. Okay, multiplying this multiplied by this, we're going to be getting 7 minus 6. This multiplied by this, we're going to be getting 14 minus 14. This multiplied by this, we're going to get minus 3 plus 3. This multiplied by this, we're going to get minus 6 plus 7. Okay, and the answer also is 1, 0, 0, 1. Okay, that's another, it's also an identity matrix. So we can see that C is an inverse of A and A is an inverse of C. So C is invertible. A is also invertible. If you take them separately, they are invertible to each. They are invertible, and then they are inverses of one another. Okay, please take note of that. Now, this is actually a theorem for square A and its reduced form AK. A is invertible if and only if AK is equals to I. If and only if AK is equals to I. Moreover, if E1, E2 up to EK is a sequence of elementary row operations that takes A to I, then the same sequence takes A to A inverse. Okay, this is what we're saying. Let me explain this theorem to you. We have A, okay, and then we perform row operation on A to get our inverse. Okay, that means we reduce A to a reduced matrix to get an identity matrix. The same row operation that takes A to A inverse also take inverse, that takes A to identity matrix, also takes the identity matrix to A inverse. The same row operation. So the same row operation that takes A to identity matrix, the same row operation that takes A to identity matrix also take identity matrix to inverse matrix, to the inverse of the matrix. So what we do whenever we want to get our inverse of A, we put A side by side with identity matrix. We put A side by side with identity matrix. Then we begin to perform roll operation on A. We begin to perform roll operation on A until we get an identity. Until we get an identity. But as we perform row operation on A, we are also doing the same row operation on I. And then by the time we get an identity matrix of A, then automatically whatever we have on this side is the inverse. Automatically whatever we have on this side is the inverse of A. So all what we need to bother with is to just reduce A to an identity matrix. As soon as we are able to do so, then whatever we have on this side is the inverse of A. Is the inverse of A. Okay, please take note of that. That's what we are going to do now. We're going to demonstrate that as an example now. Okay, so now we want to find the inverse of A given as 1022. Okay, we want to find the inverse of A using the inverse method, the inverse method. Okay. Okay, so what do we do? In order to find the inverse of A, we put it side by side with an identity matrix. So we write like this, A, and then we put an identity matrix to become one single matrix. That is now 1 0 2 2. Then we put it side by side with an identity. This is a 2 by 2, so we use a 2 by 2 identity. 1 0 0 1. Okay. 1 0 0 1. Okay. So now what we need to do is to transform this to be an identity. To transform this to be an identity. All right. So we perform row operation. This is already 1. There's nothing. There's no need to do anything on that. But these two must become 0. These two must become 0. So how do we make these two become 0? We say row 2, we are changing row 2 minus 2 row 1. Okay, and then we're giving it to row 2. Row 2 minus 2 row 1, and we're giving it to row 2. Okay, this is not changing. Row 1 is not changing, but row 2 is changing. So 2 minus 2 row 1, we have 0 there. 2 minus 2 row 1, we still have our 2 there. 0 minus 2 row 1, that will be negative 2. 1 minus 2 row 1, that will be 1. Okay, that's fine. Okay, don't forget we are changing whatever we do for this for the row, we are doing it for all of them. Okay, for all of the entries or element in that row. Okay, now we have made this to be 0. Now the next thing is to make this one to be 1. The next thing is to make this to be 1. Okay, so how do we make that to be 1? We just do 1 over 2 R2, and then we give it to R2. 1 over 2 R2, and then we give it to R2. R1 is not changing, we leave it. R1 is not changing. Then half of 0 is 0, half of 2 is 1, half of this is negative 1, half of this is 1 over 2. Okay, now we can see now that we have now changed A to identity, so we stop. Automatically, this is now identity. Automatically, this on this other side, you remember it was identity when we started. It was identity when we started, but now it's another matrix, and that another matrix is our A inverse. Okay, so I can now say A inverse equals to 1 0 minus 1 half. That is my A inverse. Okay, I can check if that is truly an A inverse. And how do I check? I multiply A with A inverse, or I multiply A inverse with A, and I should get an identity. I should get an identity. Okay, so let's check. to be able to be sure that, so we can multiply A with A inverse. So this is our A, recall, this is our A, 1022. This is the A inverse we got now, 10 minus 1 half. That is the A inverse we got now. Okay, let's multiply both together to be sure we get an identity. Okay, that will now become 1022 multiplied by 10 minus 1 half. Okay, let's multiply them together. So in multiplication, this row multiplied by this column, that will be 1. This is 0. Okay. This row multiplied by this column, that will be 0, 0. Yeah, 0. This row multiplied by this column, that will be 2, negative 2. 2, negative 2. This row multiplied by this column, that will be 1. Okay. So that is, we are going to be having 1, 0, 0, 1. Okay, you see, and this is an identity matrix. This is an identity matrix. So that shows that A is an inverse of, or this A inverse we got is the A inverse truly. Is the A inverse truly. Okay, please take note of that. So anytime you are asked to find the identity by the inverse method, you just put the matrix side by side with the identity and you begin to reduce the matrix to become an identity. As soon as the matrix become an identity, whatever we have on the other side of the matrix is the inverse of it. Is the inverse of it. Please take note of that.